This video is about using a sample to make an inference about the population. Remember that inference means we are making an informed, evidence-based decision. In statistics, a formal inference is made about a population using data from a sample. However, whenever we take a sample, there's always an element of variability in it. For example, let's say we had a collection of 800 gym membership times. In other words, these are 800 visits to the gym. We have record of how long those people were there. Now, that's our population. How long do people usually spend at the gym on average? Might be a question we try to answer with this population. Do you want to add up all 800 numbers and divide by 800? So how can we make an inference about the average without actually doing that? We take a random sample. So let's say we took our sample of 5 people and we added their times up and divided by 5. We got 56. Then we take another sample. Some of the people are different because that was a random sample. And so the mean changed slightly. It's now 52 minutes. This is called sampling error. We didn't actually make an error, but it's a recognition that at least one of these is not the true mean of the population. Sampling error is the expected error due to using a sample. That's not to say that you can't make an error. It is possible to make a mistake. We could make a mistake by calculating the mean incorrectly. Maybe we missed a number when we were adding. We could have a biased sample due to improper sampling. Let's say you just asked the first 5 people in the door. We could have copied incorrectly from the list that the gym owner had given us. Or we could have used poor sampling methods. For example, asking people how long they exercise rather than actually recording it. People are notorious for not being quite honest when you ask them how long they exercised. Now, what's the difference between a sample statistic and a population parameter? Well, a sample statistic is a measurable characteristic of the sample. So it's a question that can be answered by collecting data and anticipating variability in the data collected. A population parameter is a measurable characteristic of the entire population. Sampling variability is the range of values between sample statistics. So going back to our example of the gym membership. Every mean that we gather from each sample is a sample statistic. The actual mean of all 800 numbers is the population parameter. Should be pretty easy to keep straight which one's a statistic and which one's a parameter. SSPP. Now, sampling variability is how far apart were all those means we got. So if everybody in the class had taken a sample of 5, then we would look at the highest and the lowest of those means and find out how far apart were they actually. That's our sampling variability. The farther apart they are, the more error we have in our means. Now, what effect does sample size have on our sampling variability and our error? When we calculated the average time spent at the gym, we took samples of 5 times, but what would have happened if we had a sample of 10 times? Well, we want the value of the sample statistic to be close to the population characteristic. In other words, we wanted that mean of our sample to be close to the mean of the population. If sampling variability is low, the error will also be low. So if we had taken a sample of 10 times, do you think the variability would have changed? Would it be higher or lower? What about the sampling error? Do you think that would have been higher or lower? When using a sample mean to estimate a population mean, why do we prefer a larger sample? Why would it be better to take a sample of 10 gym times instead of 5? Well, because it gives us smaller sampling variability and a more accurate mean. So in general, we choose a larger sample so that variability will be smaller and error will be smaller. For example, choosing 10 people and then we calculate the mean of that, would have given us 54, which is actually closer to the population mean. The actual average of all 800 numbers is 53.9. So we're getting closer. Our error is getting smaller. Now, exactly how far away was each of our means from the actual population mean? Well, that leads us into mean absolute deviation. If you've ever seen MAD or MAD, that's mean absolute deviation. But we'll save that lesson for another day.